about mathematical problems in micromagnetics, paradigm for multiscale problems. So this is
Thank you very much. So, as promised, today I want to talk about an independent topic, but which is nonetheless, of course, connected to the general scheme of trying to understand multiscale problems in materials. And the problem of micromagnetism is interesting from many points of view. First of all, there are lots of experimental observations, and you see some of them. I'll say a few more words about them in a second. There are lots of computer simulations, so there's a huge wealth of data, because actually for practical problems it's a very important problem, starting from sort of how to increase the density on your disk drive in your computer. So magnetic recording has been a huge industry for a long time and continues to be strong, and there are lots of other devices which use magnetic fields. Even unusual in applications problem, there's almost universal agreement sort of what the mathematical model is which you should simulate, and it's relatively simple. Nonetheless, it has been studied relatively little by mathematicians until recently. So I think this problem also presents sort of good new opportunities for sort of interesting applied mathematics to be done. And what I want to talk about today, as far as regards my work, is all joint work over a long time with Antonio de Simone, who's now in Leipzig, Bob Cohn in Courant, and Felix Otto in Bonn, and for the experiments with Rudi Schäfer in Dresden. But today's lecture will also be more a survey talk to introduce the whole topic, so we'll also talk about some other people's work to show a bit the evolution of the field. So what is the subject matter? So what we want to understand are magnetization patterns in ferromagnetic materials. So here you see some examples, and actually all these examples come from a beautiful book by Hubert, who unfortunately died far too young, and by Rudi Schäfer. It's called Magnetic Domains, and it came out with Springer a few years ago. And it has not only sort of a beautiful collection of pictures, but also a beautiful description of the state of the art of the theory seen from a physicist's point of view. So what is special about this magnetization patterns? Well, as you may remember even from high school, sort of typically the body is not uniformly magnetized, but you have certain regions, so-called domains, where the magnetization is more or less uniform, and they're separated by relative sharp transition layers called domain walls, in which the magnetization switches. So between here and here we have an extra magnification of a factor 20, and so in this higher magnification you can see very nicely the wall. I should maybe explain the gray code. The magnetization is a vector, so what is usually plotted is one component. So for example, in the middle picture, black would be pointing down, white would be pointing up, and gray would be pointing either left or right, and with some either by taking two pictures or sort of by having some experience, you can sort of draw the arrows from this gray plots. On the next one, you see that these walls can have internal structure. In fact, what you see here, as you go from this to this, you can wind either this way round or the other way round, and as you change, you get a topological defect in the middle. So these are these so-called Bloch lines. They're called Bloch lines because the body is really three-dimensional, so in a cross-section it's a point defect, but really it's a line. And from these lines come out this interesting extra structures. They are called cross-tie in English, or in German they're called Stachelwände, because they're kind of sharp So here you have another example of these cross ties. Here you have a picture at even higher resolution, another factor 20 higher, so you see the multitude of scales on which structures exist. And so it's not only that there are different structures on different scales, but even similar structures can repeat in an almost self-similar pattern. So this is a pattern near the surface of a body. So here would be the surface of the body, and you see deep inside you have relatively large domains of almost the tens of a millimeter, and as you approach the surface they get finer, and here, this here is a blow-up of that section. So you see you have 3 or 4 generations of refinement. So that's a wonderful example of multiscale structure. So micromagnetics is not only an interesting problem in itself, but hopefully also a problem where we can try out new mathematical tools which might be useful in general for multiscale problems. So I will focus on variational problems, if you like, on minimizers or ground states, and will not talk about dynamics. And so for ground states, everything is driven by the micromagnetic energy. So omega is a domain in R3 which represents our ferromagnetic body, and then the basic variable which we want to find is the magnetization, which is a map from omega onto R3. And the usual assumption is that the length is constant because it's essentially related sort of to the atomic moment per atom. And so it's convenient to normalize the constant to 1. So really we're looking at a map with values in S2. And the important thing is that this map, through Maxwell's equation, generates an induced field, sort of, and if you choose the right normalization of units, then the induced field is simply given by these 2 sets of equations. So in other words, the induced field up to sign is the L2 projection of the magnetization onto gradients. You extend the magnetization by 0 outside the body, you project onto gradients, and that's your induced field. And the energy now has 3 contributions. One, well, these are crystalline materials, so the magnetization usually prefers certain directions, either sort of one line or the 3 axes of a cube. So that's captured by this anisotropy energy. Then the magnetization doesn't want to change too rapidly, so that's captured by the Dirichlet energy. And then there's the energy of the induced magnetic field. And then, of course, you can apply an external field which just leads to a linear coupling with M8HX dot M. So I haven't written that out in detail.
What is phi in your second term?
Okay, phi is a material-dependent function, and say, for example, for a uniaxial material it will be 1 minus m1 squared, and then the body will prefer magnetization in the E1 axis, and there's a more complicated expression if you have cubic symmetry. So it's a given function which depends on the material. So to get some first idea how this simple functional can generate this variety of patterns, let's look a bit at the terms individually. So the term which is most easy to understand, of course, is this anisotropy term. This simply says that the magnetization prefers certain directions, and I drew it in 2 dimensions here, and then the typical cases are that it's either uniaxial, so it prefers one direction, or it prefers 2 orthogonal directions. Then the term which really drives a lot of the things is this magnetostatic energy, the energy from the induced field. And to understand what that does, the best way is to understand when it will be 0, and it's 0 exactly when the divergence of m is 0 in the distributional sense. So if it's 0 inside, and if m is tangential to the boundary, so that you get no distributional component. So magnetostatic energy tries to achieve divergence 0 and tangential field. And you see, if you have cubic, if you have square symmetry, that's very easy to achieve, and you get this so-called Landau pattern. So here it's tangential to the boundary, it makes certain jumps, but if you look carefully, then the normal component of m doesn't jump. If I had reversed the orientation here, that would have been bad, because then the normal component would jump. That's what you know from high school, that magnets want to sort of connect North Pole to South Pole and not North Pole to North Pole, and that's exactly the analytic version of it. On the other hand, already, if you have a uniaxial material, already the competition of these two energies produces very interesting effects, because you want the magnetization point in this way, but that would mean that on the boundary, it's not tangential on these boundaries. It would not be tangential, so you create a lot of magnetic field there. And the way out of this is actually to make a fine scale structure. You do a structure like this, but this would cost you too much energy, because you have large regions where the magnetization is not aligned in the right direction. But simply by making this pattern finer, you can reduce the area of the so-called closure domains, and thereby you could drive the energy arbitrarily slow by making it arbitrarily fine. So actually the infimum of this problem of just these two energies would not be attained, and you would have a minimizing sequence which oscillates more and more rapidly. And now at this point, the exchange energy kicks in, the gradient term, and that on the one hand tells you that you can't have really a sharp transition, but okay, you put in a boundary layer, but it also penalizes it gives you a certain interfacial energy for each change, and therefore if you put too many, then you pay too much. So through a more subtle competition, it eventually limits the fineness of the structures, and more scales emerge. So now let's look at the functional a bit more from the mathematical side. So I've copied the functional here, and I've now written Maxwell's equation in the symbolic form. You first take the divergence, then you invert the Laplacian, and then you take the gradient. So that would exactly be the projection onto gradients. And if you look at this sort of with the naive mathematic eye, you see that the highest order term is this Dirichlet term. This term is order 0, and this term is also order 0. It's a pseudo-differential operator, but it's order 0. So you are trained to look always for the highest order term, because the rest is a compact perturbation. So you'd say it's essentially a compact perturbation of the harmonic map problem, Dirichlet energy plus a constraint. But if you want to really understand the patterns I showed you, that turns out not to be the right point of view, because you have to look what the coefficient in front of the highest order term is. And if it has dimension of length, and if you look at it sort of for a variety of materials, then it's usually in the range of a few nanometers, few times 10 to the minus 9 meters, whereas the patterns you're looking at occur on the scale typically of micrometers and above. And on that scale, this term has almost no direct influence. So even though it's the highest order term, the true patterns are actually mostly driven by this non-local term, by this magnetostatic energy. And just to give you an idea what the typical length scales are, you already saw them in the picture. So for example, for iron, which is a standard ferromagnetic material, the domains can go up to 10 microns. The block walls sort of are on a scale of a few 10 microns. The block lines are almost 1 order magnitude below, and then you can have something like a sort of point singularity for a harmonic map. Well, it's not quite a point singularity, but it's smoothed out almost on the atomic scale. I mean, 1 nanometer is like 10 atomic spacings. So that's just to emphasize the multiscale character. Now, what is kind of, or what, yes?
The mathematical equation, which probably is derived, doesn't take into account atomic structure.
No, that's right. I didn't say that explicitly. It's what physicists would call the mesoscopic model. The origin of these different energy terms is, of course, of an atomistic kind. For example, this exchange energy, which penalizes changes, comes ultimately mostly from the spin-orbit coupling of the atoms. But all the length scales are still relatively large to the atomistic spacing, so this mesoscopic theory seems to work very well. And in fact, experimentalists are quite happy with that. I remember we once had a discussion with Schäfer about sort of how to measure a certain quantity, and sort of then there were sort of different experimental possibilities, but they all had advantages, and then in the end he just said, well, if you really want to know it, why don't you just compute it? So that's, say, maybe unlike sort of Navier-Stokes equation and turbulence, where sort of everybody has a different turbulence model. Here, people really seem to trust in this equation. So what is the state of the art, if you like, in the physics literature and electrical engineering literature on this problem, which is huge? Essentially, what people did is they looked at these patterns and they come up with constructions of approximate solutions or test functions, if you like, for the energy, which in the mathematical language would give very good upper bounds for the energy. And there are lots of simulations, but simulations are tricky because it's a non-convex problem through this constrained length equals 1. It's non-local through this induced magnetic field, and there are many length scales which you cannot resolve all simultaneously on a computer, so you have to make compromises. And there are kind of a number of ad hoc theories which are simplified and which are supposed to capture behavior on certain scales, or sometimes they're seen as different physical models. So what do we see as the mathematical challenges? So often there are small parameters. For example, this exchange length is a small parameter, or many magnetic systems are thin films naturally. For example, recording, you're always talking about a very thin film, so that the aspect ratio would be a small parameter. So one issue is to sort of find optimal scaling laws, say, for the energy with respect to certain small parameters. And often good candidates for upper bounds are known, but what is often missing is to show that really there's no better construction. And I mean, as you see from some of the complex microstructure, I mean, it's not so clear that there could not be something complicated which does better. So what one needs is methods for lower bounds. Then one wants to identify sort of different scaling regimes, and then say in particular, if you think of computation, when you will have very complicated structure, so you would like to know which quantities are robust and which may sort of change a lot if you make a small change of the conditions of the parameters. And somehow mathematical robustness is closely related to compactness. You have some quantities which may only converge weakly, so they may remain highly oscillatories, and other quantities may converge strongly. And okay, then sort of a more ambitious theory would be to actually derive limiting theories in certain regimes, and maybe ultimately you would like to sort of build up a hierarchy of theories which capture the behavior of different scales, and then you have links between them. And as I said, I will not discuss dynamics. I will not even discuss hysteresis, which is related to local minimizers. So there's something which one could do, but I mean not in this talk. So the first thing I want to address is what is called, would be called in the physics literature, the large body limit. So this corresponds to the situation when the body size is large compared to this intrinsic length scale, the exchange length. And of course, as mathematicians, it's much easier to let W go to 0 than let the domain go to infinity, and upon rescaling, that's the same. So that was investigated by Antonio de Simone in his thesis and independently by Luc Tata. And here is the result. So as you let W go to 0, the functionals converge in the sense of gamma convergence. I repeat that notion in a second. And the limit problem, well, not surprisingly, the Dirichlet energy drops out because its coefficient became 0. But the other effect is that the anisotropy energy has to be replaced by its convex envelope. And you should understand that in the sense that this also includes a constraint. So here it's convenient to incorporate the constraint into here by saying that the energy is plus infinity if you violate the constraint. So in the limit problem, you only have an inequality constraint. You get a convexification. And so just to recall, so the notion of gamma convergence is a good notion for the convergence of functionals. So on the one hand, you require something like joint lower semi-continuity, and then you require that this functional I in some sense is the biggest functional with this property so that you can recover it by a suitable sequence. And the relevance of gamma convergence is that there's a kind of soft meta theorem which says that gamma convergence is essentially equivalent to the convergence of minimizers. And so what is interesting in this large body limit, I mean, those of you who have a bit of experience with lower semi-continuity or functionals and so on, they will not be surprised to see the convex envelope of phi here, because once you have no constraint on the Dirichlet integral, you can make arbitrary oscillations, and oscillations are like mixtures, so by Jensen's inequality, the convexification is a lower bound, and you expect to be able to achieve that by Carat-Theodoris theorem. But the interesting thing is that sort of that you can make the oscillations to achieve this relaxation, this reduction in energy, without adding extra energy here. I mean, it could well be that sort of when you make these oscillations, then that this could introduce extra energy in the magnetic field. And in fact, it turns out that it depends on how you make the oscillations. If you make them in the wrong way, that you get locally a lot of pole-to-pole interaction, you will have extra energy. But what de Simone and Tata proved is there's always a way to do it so that you don't get extra energy coming from here. So the second example I want to talk about is addresses this problem of refinement of structure towards the boundary or domain branching. And that was investigated by first by Schoxy and Cohn in 2 dimensions, and then together with Otto for the full 3-dimensional problem. And in the physics literature, sort of there were earlier discussions of that in the sense of upper bounds. And sort of their work builds a bit on work which Cohn and I did on branching in this martensitic, in this solid phase transformation structure. So what's the issue? So to sort of get to the core of the issue, we take sort of a rectangular block of length 2L and of cross-section 1. And to make life a bit simpler, in the cross-sectional variables, we work with periodic boundary conditions. And the interesting boundary is this lateral boundary here, the plane x1 equals 0. The functional is essentially the same as before, except we slightly simplified the exchange term. Instead of having a second derivative, we only put a first derivative, and the effect of this is that you don't need to make a smooth transition layer, but you really can make a sharp jump, and then you're penalized by the height of the jump. So this is understood in the sense of a BB norm. And sort of that makes life a bit simpler because you can work with sharp interfaces and you don't have sort of to smooth out the interfaces at each step, but it's supposed to capture essentially the same physics, namely that each jump costs you a certain amount per surface area. Then the important thing is the interaction between these two terms. So this is made in such a way, remember that m has always unit length, so this prefers to have m1 to be 1 and m2 and m3 to be 0. m1 can be plus or minus 1. But you see that that's unfavorable at this boundary, because m1 being the 1 means that you sort of have magnetization perpendicular to the boundary, so the distributional divergence is not 0 there, and you introduce a lot of magnetic field. And the way to reduce that is sort of to oscillate rapidly between +1 and -1 near the boundary, because then here you see only some kind of weak limit and you get a reduction of energy. Or if you think physically, this kind of loops, they close up between the plus and the minus region. So that's what drives this thing, and here is the result that they could prove. So the experimental observation which you saw in the pictures, that sort of they're very fine domains in this basal plane here, and they're kind of indicated by this shapes there. So, and the theory, so the results they prove is, first of all, there is a construction which gives an upper bound which scales with this small length scale to the power 2/3. They could also prove there's a lower bound with the same scaling, and what they could show in addition is that when you use a structure which is uniformly fine, so which is not only fine in the basal plane but which is also fine inside, then you get a non-optimal exponent. So that's evidence that there must be something happening, some refinement happening towards the boundary. And so I don't want to go into the details there, but sort of one key point is to derive a new interpolation inequality which uses BV, the exchange energy, uses the fact that you have unit length, and uses the fact that the magnetostatic energy is related essentially to the h-1 norm on the interface. So the last example, which I want to discuss in somewhat more detail, concerns the regimes of thin films, which is how most magnetic materials are made, in particular in recording. So here is the setup. So say you have a film which is a cylinder, you have a certain base domain, little omega, and it has side height d, and later we will also allow to apply a certain external field in the plane of the film. And then the energy can be written in this way, so that's the same energy as before, except that I introduced certain new non-dimensional parameters. And so what are the basic non-dimensional parameters? So one is the aspect ratio, thickness over diameter. So we're thinking of a thin film, so say a typical aspect ratio for a realistic film would be 50. Then these films for recording are usually made out of material which only have a very weak anisotropy. You could almost put it to 0. So for permalloy, it's something like 10 to the -4. So it's even much smaller than the aspect ratio. And then there's another natural parameter which has to do with this W before the Bloch line with the intrinsic material parameter compared to the thickness of the film. And that for the films one usually studies is roughly speaking of order 1. So before I state the theorem, I want to sort of say a bit what one expects for the hierarchy of the energy landscape in such a situation. In fact, I have 2 slides for this. So maybe I put this up at the same time. This is a bit small, but has nice pictures. So there are several things, there are several possible contributions to the energy. So one is that the magnetization could change in the X3 direction, in the sin direction. That will clearly cost you a lot of energy because there's a gradient there. Then what also costs a lot of energy is when the magnetization points out of the plane, because you generate all this divergence there. In the electrostatic analog, it's like generating a charge on the top and bottom surface, so that generates a lot of field. Something which also generates energy, but not that much, is when your magnetization is not tangential to the boundary of the two-dimensional domain. There you can see you only generate a logarithmic amount. Then there are some things which generate a moderate amount of energy, namely the divergence which comes sort of simply from slow in-plane turning of the field and the interaction with the external field. And then there are other things. For example, you saw these vortices, or you saw these walls where the magnetization turns very slowly. These turn out to be of higher order. So that's what one expects kind of from back of the envelope calculations, and that's sort of exactly in the spirit of the physics literature. You put in a certain pattern and sort of you compute its energy and you see what happens, and this gives you some idea what happens, but it doesn't prove anything. So what we were able to prove is the following, and maybe I bring back the slide with the original formulation so you can see the parameters. So what we could prove rigorously, you can see here. So we look at a regime where the aspect ratio is small, where the film is very soft. You can even take Q equals 0. And then we have a very large regime for this parameter kappa, ranging essentially from d to 1 over d up to a logarithmic factor. And in this regime, we can rigorously compute the gamma limit of the energy after suitable rescaling. And the effect of this gamma limit is that the things which have high energy become constraints. So this you have to make perfectly happy. So in particular, the limit problem involves only fields which are independent of the thickness direction. So I can view them as fields defined on a two-dimensional domain. And the limit problem also involves only fields which have 0 out-of-plane component, because that simply costs too much energy. And the limit problem also involves only fields which are tangential to the two-dimensional domain on the boundary. So these are the constraints. And then the only energy left is essentially what comes from the magnetostatic part. And everything else drops out. And the constraint, as in the De Simone theory, turns out to be relaxed. So what you're left with is a quadratic functional with sort of a quadratic inequality constraint. And the induced field is now computed in principle in the same way, except that you now have to imagine that this in-plane divergence simply generates a surface charge. So you compute the potential generated by this charge, and then you compute the energy of the field coming from this potential. And when you look at this a bit closer, you see that actually this problem, this is convex, and it's strictly convex in the divergence, because the divergence directly enters into here, but it's not strictly convex in the full M. So in terms of the questions about robustness, that's one thing you learn. The divergence is uniquely determined, but the M itself on the level of this limit problem is not uniquely determined. And let me just say one word about the proof. So for the gamma convergence, you have to prove an upper bound and a lower bound. The lower bound is essentially a standard lower semi-continuity argument. And The upper bound would be very easy, namely you say you take a field here and assume for a moment it had even in addition unit length, and then you would simply extend the trivial in the x3 component, and that would be it. But as you may have seen already, satisfying all these conditions is actually topologically impossible. You cannot have a field for simply connected domain which is tangent to the boundary, has unit length, and is in H1, because such a field will have a point singularity, and that just fails to be in H1 by a logarithmic amount. Or you can say it in another way, H1 functions do allow to have a degree, even though they're not continuous, but the degree is essentially something homological, and that's still okay, and then you get a contradiction with the boundary conditions. So this is topologically impossible, so you need to introduce vortices, and you need to treat them very carefully. And also in general, you don't have a unit vector field to start with, but a field which has length less than 1, and so what you need to do is you need to approximate it by a structure of domain and walls, and then you have certain point singularities, and there you insert these vortices where the magnetization has to go out of plane. So, and what I'm telling you is that it can be done, but I won't bore you with the details. And one crucial fact is that you really use that H1/2 does not embed into L infinity in one dimension to sort of put in the right kind of nail wall. So you can make a transition turning from here to here with arbitrarily low energy. Okay, so one good way to understand this reduced limit functional, which is much simpler than the original one, is to look at the Euler-Lagrange equation. And since this is a quadratic problem, I mean, they are very simple. In fact, the nice way to write them is you look at the external field, and on the other hand, you can look at the in-plane component of this induced field. And the Euler-Lagrange equation, if there was no constraint, would be that this is 0. And since you have an inequality constraint, when this gets active, you have a Lagrange multiplier. And so from this, you see immediately that you have 3 different regimes. When you apply no external field, what you want is that the induced field is 0, and that simply means that the divergence, the in-plane divergence, has to be 0. So that's very simple but important regime, and that's in the physics literature that's known as the principle of pole avoidance. So you don't have pole-pole interactions. Then there's a next regime, which is a regime where the Lagrange multiplier is not active. So that works up to some kind of critical applied field, and that's known as field expulsion, because then the induced field can be used exactly to cancel the applied field. And then there's a supercritical regime, which is known as field penetration. And I should mention that 1 and 2 were sort of derived by physicists on kind of physical intuition using some electrostatic analogy, but the regime 3 was not known, and in particular it was not known that sort of all these 3 regimes come from the same variational principle. So the derivation of the physicists here, if you like, was not variational. And so what the limit theory determines uniquely is the divergence, that therefore determines uniquely the induced field, and it actually also determines uniquely the region where lambda is non-zero, because that's determined by the field alone. It doesn't depend on M. But M itself is not uniquely reconstructed, and so how would one uniquely reconstruct M? And here are 2 mathematical conjectures which are still open, even though they're plausible. So gamma convergence goes for the limit of arbitrary sequence with the right energy scaling. if you take a sequence of true minimizers of the epsilon problem, you could expect to have better results. And so one conjecture is, for example, that if you take true minimizers, you will actually not relax. So you will have strong convergence of the magnetization. But that's an open problem. Sort of by analogy with some other problems where this has been solved, there is some hope that this might be true, but it's open. And the second conjecture goes even further. It says when you kind of not only look at this term, but you look more carefully at the next order corrections, then you might be able to select between different of the non-unique solutions of the limit problem. And it would be natural that the next order term somehow is related to some interfacial energy coming from the regions where the magnetization jumps. That's sort of what the physics would suggest to you, but that again, mathematically is not known. So what is known sort of is something which is closely related to this first conjecture. And so the result is proved for a slightly different, let me swap this because this one is better. The result is proved for a slightly different functional, but which has strong analogy. So let's first look at the new functional. So here the variable is u, and we have a first gradient and a second gradient. It's also, u is also defined on a two-dimensional domain, and the assertion is that if this energy is bounded, so or even weaker if these two conditions which follow from this by the arithmetic geometric mean inequality, so if this energy is bounded, then the corresponding sequence is actually relatively compact in L2. And the analogy with magnetism is you should look at m as the rotated 90-degree rotated gradient of u, then the divergence of m would be exactly 0, and this term measures the non-plane, the out-of-plane component of m. What we want to study is kind of dual. We want that the out-of-plane component is exactly 0, and the divergence may not be exactly 0, but there's a strong tendency when it's not 0. So the two things are closely related, but they're not the same. So here you're assuming the divergence is exactly 0, and there's a strong penalty for the out-of-plane component, and you have compactness, and the other problem would be just the other way around. And yeah, I can show you just a very brief idea of the proof. So it's strongly inspired by the work of Tata and Müller on compensated compactness and their applications to conservation laws. So the idea is to identify quantities which are well behaved, say if you have a field which is exactly a gradient and which is exactly a unit vector field. Then you want that the curl of this nonlinear quantity is also 0. So, and that's an algebraic problem. I mean, yeah, you apply the chain rule to this and you play a bit around with this, and you can characterize this family of functions explicitly. Then what you want to show is that now if UK has curl 0, but not quite unit length, that then still the curl of this quantity is well behaved in the sense that it's compact in h-1. So that's something which you have to check from these two conditions. And then you can use two of these what we call entropies, and you can use the diff curl lemma to get that certain nonlinear quantities can pass to the limit, and that gives you restrictions on the possible oscillations. And one way to do this is to sort of use the Young measure, just as Luc Tatar did for conservation laws. And actually, very recently, there sort of has been an interesting development in this, which I don't have time to discuss in detail, but which I want to mention. So originally, we used ideas from conservation laws to sort of get the compactness theorem here. Now, later, people realized that you could turn these things around, and you could use some other facts which we learned on this problem and on other problems in the calculus of variations to get new results in conservation laws. And there are currently two very active teams. One is Delelles, Otto, West-Stickenberg, and one is Ambrosio, Kirchheim, Lecumberri, and Riviere, and they now do also recombinations like in molecular biology. And essentially, sort of their results are of the type that you can get solutions which behave like sort of functions of bounded variations, in the sense that you have certain rectifiable sets where they're jumps, and on the complement they're more or less continuous, in a setting where you can't have to have really BV bound. So it uses weaker bounds and sort of very subtle geometric measure theory arguments. So that was just an aside. So, well, we were also interested to use our reduced functional to do computations, because for the full three-dimensional problem, computations are very expensive, in particular when you want to do relatively wide bodies, because in principle you have to always resolve the finest scale, which is a few nanometers, and if your specimen is 100 micrometers, then you can just not afford it. I mean, people can do maybe sort of 1 micron in size, but already that's difficult. And so there we do the following. We first find one solution of this two-dimensional problem. That's a convex problem, so that's, I mean, very robustly to solve by standard methods. And of course, in general, this will not have unit lengths, but to compare with experiments, we want to have unit lengths. And how do we make it unit length? Well, we simply, and we want something which has still the same divergence, so that the energy is the same. And we do that simply by solving, adding a rotation of a gradient, and then that means we have to solve a certain Hamilton-Jacobi equation. And for this, we take the viscosity solution. Really, the solution which we should take is something which minimizes a certain interfacial energy, but since we don't yet know what this is, the viscosity solution also has the effect that it doesn't make, so to speak, unnecessary oscillations. So that's a good candidate, but you can show that in pathological domains, I mean, it may not always be right, but for convex domains, it seems to work quite well. So in this way, what we achieved, we originally had one rather difficult non-convex problem, and we now have two problems which one can compute robustly. And so, if you like, the sort of, and we believe that this is a kind of successful approach also for other problems. We've used it for pneumatic elastomer, for example, to combine analysis and computation. We somehow use analysis to extract some essential feature to reduce a problem to a core. Then we can solve that core problem, and then we somehow can use analysis to go back to understand sort of the more detailed structure. And okay, so now you may wonder how this works in practice. So here's a computation. So this simulates the following situation. You have a square-shaped domain, and first you have no applied field. Then it likes to form this closed flux structure which you saw before. It wants to make the divergence 0, and it wants to be tangential to the boundary, so it naturally developed this structure. Now you apply a field at 45 degrees to the sides of the square, and that means the magnetization wants to align with that field. So that means that these two regions, which have positive scalar product, are favored, whereas these two regions are disfavored. So, and you can see what happens is that these two regions grow, and of course also the magnetization will turn a bit towards the field, but because of the boundary, it still has a strong tendency to point in that direction. And as you increase the field more and more, this kind of vortex gets pushed more and more to the boundary. And here, for example, for the first time, this region here becomes disconnected. Okay, so we did the computation first, and then we asked Rudi Schäfer in Dresden to do the experiments. So here are the experiments. And I should say there is no no fiddle parameters anymore. Once sort of you look up in your handbook the material parameters and the size of the specimen, you non-dimensionalize everything, and then you have no adjustable parameters. There's some uncertainty, of course, in the material parameters because you cannot measure them to sort of 1%, but we took sort of the best values which were available. And you see there's not only a very good qualitative agreement, but there's in fact also quite good quantitative agreement. Quantitatively it's about 10% off. So this brings me to the summary, which comes in 2 parts. So I hoped I could illustrate you a bit that this relatively simple micromagnetic energy, which is essentially the Dirichlet energy plus a non-local term, can lead to sort of complex behavior with many scales, and therefore it's sort of a good example to develop mathematical techniques on a problem which is relatively clean. If the multiscale behavior comes from the fact that there are really sort of 5 scales in the formulation of the problem, then it's very hard to extract some clean mathematical feature. And I hope I could convince you that variational methods can be useful in analyzing this. And I think it's clear that there are many open problems. For example, understanding the details of the wall structures in more detail. So that's currently going on. And there's, for example, some beautiful work by Alouche, Rivière, and Serfati. And so the second part of the summary says that so these multiscale problems occur in a number of other contexts, and sort of what I personally view as a challenge for applied mathematics, and in some sense also for computation, is to identify the right mathematical objects which sort of capture essential information and can be robustly determined and also robustly computed. I mean, if you have a problem which has a very complicated pattern formation, you do a computation, you'll see a very complicated pattern. But you don't really know without analysis sort of what part of the pattern would be completely different if you do the calculation with slightly different parameters, and what is kind of structurally robust. So that's where I hope that sort of developing these analytical tools can bring some insight. And with this I would like to close and thank you for your attention. Yes.
You mentioned before these fine structures actually replicate themselves. It's like fractals?
Yeah, so, okay. There's many things which one could say. So fractals are usually supposed to be self-similar. These structures may or may not be self-similar. For this other problem which came from solid-solid phase transition, actually Kohn and I could do a little bit, and then Sergio Conti could prove completely that they're self-similar in some asymptotic sense. So when you do the natural rescaling, then the rescaled objects for a subsequence at least converge. The other thing is, of course, these structures are never infinitely fine, but there's a cutoff scale, but okay, one can idealize and one can sort of let the scale go to 0. And then yeah, maybe the last thing is sort of the way what I see in terms of publications on fractals is mostly on the kind of descriptive level, so to speak. I mean, one doesn't try to understand usually why they arise or whether there's a kind of variational principle which produces them, but one more tries to sort of describe their features or compute certain scaling exponents. So that's what I think is sort of different in kind of terms of attitude. We start from a variational principle and we see what that produces.
So maybe a suggestion on one should be doing fractals.
Well, I mean, yeah, so for example, when you say, I don't know, the human body is a fractal because you have all these organs which are, I mean, have complicated self-similar structure, I mean, that's okay, it's only a finite number of scales, but on that finite number of scales, it may well be a true statement, but what do you learn from this? I think what you would really like to understand is why it has a structure, and it must somehow be related to the functions of the organs. Yeah, so they're studying a problem in a two-dimensional domain, where also in the formal limit problem you would have this difficulty that the boundary conditions are not consistent with the fact that you want H1, and so you regularize the problem and you find that the minimizers form singularities at a finite number of points, and that's determined by the degree, and you can sort of subtract the logarithmic part of the energy and get some renormalized energy. So the regime I was talking about here is not dominated by vortices. It's dominated by the non-local part of the energy, by the magnetostatic energy. So vortices in this regime, which I studied here, turn out to be of lower order, so they disappear in the limit. We're studying other regimes which correspond to much smaller bodies, where vortices become important, and then we get sort of similar but different results, because still this non-local energy plays a more dominant role, and that sort of doesn't exist in this more conventional Ginzburg-Landau ansatz. But it's a matter of regime. In some regimes, vortices are important. In other regimes, other things are important. And sort of for the typical film size, like the one Schäfer has in his lab, vortices are not important. Doesn't play such a dramatic role because it really sits in front of a lower order term. And yeah, if you let first Q go to 0, that's a very regular limit. So you could do that. And sort of for the realistic. Yeah, but as long as Q goes to 0, it almost doesn't depend on sort of how fast it goes to 0. So it has to go faster to 0, faster or at least as fast sort of as the aspect ratio. But for example, for permalloy, that's certainly true because Q is of the order 10 to the minus 4. You can study other limits where somehow in the rescaling Q becomes very big. That's what they use for permanent magnets, and then you get into other regimes. Actually, sort of one thing I learned here, it's very different to have a singularly perturbed problem with one small parameter and with two small parameters, because with two small parameters you have many possible combinations, and part of the work here actually was to figure out sort of a regime which was kind of interesting, so which capture a broad amount of physical phenomena, and which could also where we could also do some analysis. I mean, there's many other regimes which you could look at, and sort of letting Q go to infinity, for example, is one, because then you sort of essentially are constrained to the 0 sets of phi, and you have to live with the rest of the energy.